Imagine you have a magic box. You put in some information about something like data about past events or characteristics, and the box tells you whether that thing will happen or not. It gives you a prediction based on the input data. Sounds cool, right? That's the basic idea behind logistic regression. It's like having a statistical crystal ball. It's a powerful tool used in statistics and machine learning to predict the likelihood of something being true or false, a yes or a no. This binary outcome is what makes logistic regression so unique. Let's say we want to predict whether a student will pass an exam based on the number of hours they studied. We can gather data from past students and their study habits. Logistic regression can help us do just that. By analyzing the data, it can identify patterns and relationships. It takes in the study hours as input and gives us the probability of passing the exam as output. This probability can then be used to make informed decisions. This powerful technique finds its use in various fields, from healthcare to finance and beyond. For instance, in healthcare, it can predict the likelihood of a patient developing a certain condition. From predicting diseases to identifying fraudulent transactions, logistic regression is invaluable. Financial analysts use it to detect anomalies in transaction data. Logistic regression plays a crucial role in making sense of data and making informed decisions. Businesses rely on it to forecast trends and make strategic choices. In the following sections, we'll dive deeper into the workings of logistic regression. We'll break down the steps involved in building a logistic regression model. We'll explore the mathematical concepts behind it, such as the logistic function and how it transforms linear combinations into probabilities. We'll see how it differs from linear regression, which predicts continuous outcomes, while logistic regression predicts categorical outcomes. And finally, we'll even build our own model using Python. By the end, you'll have a solid understanding of how logistic regression works and how to apply it to real-world problems. You might be wondering, why can't we just use linear regression for this? After all, it also deals with relationships between variables. Well, here's the catch: linear regression tries to fit a straight line through our data, predicting a continuous output. But we're dealing with probabilities here, values that lie between 0 and 1. A straight line doesn't quite cut it for probabilities. Imagine the line extending infinitely in both directions. It could end up predicting probabilities less than 0 or greater than 1, which doesn't make sense. This is where logistic regression comes in with its secret weapon, the sigmoid function. This function acts like a gentle curve, gracefully mapping any input value to an output between 0 and 1. It's like fitting a snug curve to our data points, ensuring that our predictions always stay within the realm of probabilities. The sigmoid function is the heart and soul of logistic regression. It takes any real number as input and squashes it into an output between 0 and 1. Think of it like a magic shrink ray that compresses infinite possibilities into a finite range. The formula for the sigmoid function might seem intimidating at first, but it's actually quite simple. It's just a fraction with a constant e, Euler's number approximately 2.718, raised to the power of our input variable. This S-shaped curve is what gives logistic regression its power. Values closer to negative infinity get mapped to probabilities near 0, while values closer to positive infinity get mapped to probabilities near 1. This ensures that our predictions always remain within the bounds of probability. Let's peek under the hood and understand the mathematical engine driving logistic regression. Similar to linear regression, we have an equation that relates our input variables, like study hours, to our output, probability of passing. The equation multiplies each input variable by a corresponding weight, representing its importance in influencing the outcome. These weights are learned by the algorithm during the training process. The sigmoid function then takes this weighted sum and transforms it into a probability. Don't worry if the math seems a bit overwhelming right now. The key takeaway is that this equation allows us to model the relationship between our input variables and the probability of our desired outcome. Section 5. Cost of misjudgment. Understanding the loss function. Like any good student learning from their mistakes, our logistic regression model needs a way to measure how far off its predictions are from the actual values. This measurement is crucial because it helps the model understand the extent of its errors and guides it on how to improve. This is where the loss function comes in. The loss function serves as a critical tool in the model's learning process, providing a quantitative measure of the model's performance. It acts like a strict teacher, penalizing the model for incorrect predictions. The more significant the error, the harsher the penalty, pushing the model to strive for better accuracy. In logistic regression, we use a special type of loss function called the binary cross-entropy loss. This function is particularly suited for binary classification problems where the outcomes are either 0 or 1. This function calculates the difference between the predicted probability and the actual value, 0 or 1, for each data point. It then aggregates these differences to provide an overall measure of the model's performance. The goal is to minimize this loss, bringing our predictions as close as possible to the true values. By doing so, the model becomes more reliable and accurate in its predictions. The model learns from its errors and adjusts its weights accordingly, striving to make more accurate predictions in the future. This iterative process of learning and adjusting is fundamental to the model's improvement. It's like practicing for an exam. The more we practice, the better we get at answering the questions correctly. Similarly, the more the model trains and learns from its mistakes, the better it becomes at making accurate predictions. Section 6. Python in action, building a logistic regression model. In this section, we will dive deep into the practical aspects of implementing a logistic regression model using Python. Now comes the exciting part, putting our knowledge into practice. We will take you step by step through the process, ensuring you understand each phase of building the model. We'll be using Python, a popular programming language for data science, to build our very own logistic regression model. Python's simplicity and extensive libraries make it an ideal choice for this task. And what better dataset to use than the famous Titanic dataset? This dataset is well known and provides a great opportunity to practice logistic regression. First, we need to load our dataset and do some basic data cleaning and preparation. This step is crucial as it ensures the quality and reliability of our model. This involves handling missing values, which can significantly impact the performance of our model if not addressed properly. Converting categorical variables into numerical ones, as machine learning models require numerical input to process the data effectively, and splitting our data into training and testing sets. This allows us to train our model on one portion of the data and test its performance on another, ensuring it can generalize well. Next, we'll create our logistic regression model using a library like scikit-learn. Scikit-learn is a powerful tool that simplifies the implementation of machine learning algorithms. This library provides pre-built functions for training and evaluating machine learning models, making our job much easier and more efficient. We'll feed our training data to the model and let it learn the relationships between the variables. This training process is where the model identifies patterns and correlations in the data. Once our model is trained, we can use it to make predictions on our testing set. This step is crucial to evaluate how well our model performs on new, unseen data. This will give us an idea of how well our model generalizes to unseen data. By comparing the model's predictions to the actual outcomes, we can assess its accuracy and reliability. Section 7. Testing the waters. Evaluating our predictive power. After training our model, it's time to put it to the test. We'll use our testing set data the model hasn't seen before, to see how well it predicts whether a passenger on the Titanic survived or not. We'll use metrics like accuracy, precision, and recall to evaluate our model's performance. Accuracy tells us the overall percentage of correct predictions, while precision and recall focus on the model's ability to correctly identify positive cases, survivors in our example. By analyzing these metrics, we can get a good understanding of our model's strengths and weaknesses. We can then fine-tune our model by adjusting its parameters or trying different data pre-processing techniques to improve its accuracy. Section 8. Real-world wonders applications of logistic regression. Logistic regression isn't just confined to classrooms and textbooks. It's a powerful tool used in a wide range of real-world applications. In healthcare, it predicts the likelihood of diseases like cancer or heart disease based on patient data. In finance, it detects fraudulent transactions by analyzing spending patterns and identifying anomalies. In marketing, it predicts customer churn, the likelihood of a customer discontinuing a service, and helps in taking proactive measures to retain them. In image recognition, it classifies images, such as identifying whether an image contains a cat or a dog. These are just a few examples of how logistic regression is making a real-world impact. Its ability to handle binary classification problems makes it a versatile tool in various domains. Section 9. Conclusion. Your journey into the world of predictions. Congratulations on embarking on this journey into the world of logistic regression. We've covered a lot of ground, from understanding the sigmoid function to building our own model in Python. Remember, this is just the beginning of your exploration. There's much more to learn and discover in the realm of machine learning. As you delve deeper, you'll encounter more complex concepts and techniques that build upon the fundamentals we've discussed here. But for now, take pride in what you've accomplished. You've gained valuable insights into one of the most widely used classification algorithms, equipping yourself with the knowledge to tackle real-world problems involving predictions and decision-making.